We are in section 1.2, the graph of a function. Any point P on a plane can be associated with a unique ordered pair of numbers x, y. And right below that, the first thing that we have is the different quadrants on a coordinate plane. And so you have quadrant 1, which everything is positive, and a lot of times we're dealing just with quadrant 1 for business calculus. Quadrant 2, quadrant 3, and quadrant 4. In addition, we have our x-axis, our y-axis, and also our origin, which is at 0, 0. The example right next to this says plot the following ordered pairs on the xy plane and state which quadrant the point lies in. So the first point that we have, x is 0 and y is equal to 4. So x goes left and right and y goes up and down on our coordinate plane. And so 0, 4, I'm going to go ahead and label that A. This is not in a quadrant. This one's actually on your y-axis. B is negative 3, 0. Which again, I'll put my point there. This again is not on a quadrant. It is on the x-axis. C is 2, 3. So we're going to go right 2 and up 3 from the origin. I'm going to label that C. Point C is in quadrant 1. And then D is negative 4, negative 1. And I'll label that D. And negative 4, negative 1, or D, is in quadrant 3. And then the last ordered pair that we have is E, which our x value is negative 1 and our y value is 4. So putting a point there, and I'm going to label it E. And this is in quadrant 2. So point E is in quadrant 2. On the top of the next page, we have the distance formula. So the distance between 2 points x1, y1 and x2, y2 is given by d equals the square root of that difference between those x values squared plus the difference between the y values squared. And we have an example that's going to use that distance formula right below. The example says find the distance between points negative 2, negative 5 and 1, negative 3. So I'm going to call the first ordered pair x1, y1 and the second order pair x2, y2. And so d is going to be equal to the square root of, and the formula is listed right up above. It's going to be x2, which is 1, minus x1, which is negative 2, squared, plus the difference between those y values, which y2 is negative 3, minus y1, which is negative 5, squared. From here, we have the square root of, and simplifying this, we have 1 minus negative 2, or 3 squared, plus negative 3 plus 5, which is going to be 2 squared. And simplifying more, we have 9 plus 4, which works out to be the square root of 13. And we're unable to simplify that radical. The example right below says sketch a graph of the function and determine the domain and range. So we do need to find the domain and range and then also sketch. This is called a piecewise function, and the domain for that first equation only works if x is less than negative 1. The next part says y will equal 3 if x equals a negative 1. And then that last function that we have, which is y equals x squared, which is a parabola, only is if x is between negative 1 and 2. So the first graph that we have is y equals x plus 1. The second graph is going to be y equals 3. And that third one is going to be y equals x squared. Again, remember f of x is the same thing as y. And so I'm going to go ahead and set up my coordinate plane over here on the right. And I'll go 4 each direction. And the first graph that we have only is if x is less than negative 1. And so for that, the graph is going to be a straight line. we have it starting at -1. It also does not include -1, so it would be an open circle there. And substituting in -1 plus 1 is 0. So I'm going to go ahead and put an open circle there. And anything smaller than this is going to make that linear line. And so we have substituting -2 plus 1 is -1. -3 plus 1 is -2. And from here we can draw our straight line continuing on for all values x less than -1. The next equation that we have is y equals 3, and this is only if x equals -1, which you'll notice is actually just a point. This is an ordered pair. We have -1, 3. So I'm going to put a point at -1, 3. And then the final equation that we have is y equals x squared, which is a parabola, which again, we're only going to be doing this graph for -1 to 2 for our x values. So substituting -1, -1 squared is 1. Again, we do not include that, so it will be an open circle there. Substituting in 0, we get 0. Substituting in 1, we get 1. And then substituting in 2, we get 4. And it is including that value, so I will have a closed circle there. Connecting this to make my parabola. And so this is our piecewise graph for this function. Note down here below the next example is the vertical line test. And it says a curve is a function if and only if no vertical line intersects the curve more than once. So you can see with this example, if we were to draw a vertical line anywhere on this graph, it would never intersect the graph more than once, even at the value of x equals -1, since we have 2 open circles and 1 filled in circle. So this also asks for the domain, and I'll write a D for domain, and a range is R. And so the domain is going to be the x values, and this is not all real numbers here. It does go from -infinity, but we do stop at 2, and we include 2, so I'll use a bracket. Your range are going to be your y values, and it looks as though that graph of our linear line on the left is going down to -infinity. And the largest y value that we have is 4, and we are including it, so I will use a bracket. The next example, I'm going to go ahead and circle, and we'll look at this one together in class. Right below the vertical line test, we have the x and y intercepts. And so an x-intercept is where the graph crosses the x-axis, and a y-intercept is where the graph is going to cross the y-axis. Steps for finding these intercepts are definitely something we need to know. This is also a way to graph linear equations. And so the x-intercept for this, we're going to set y equal to 0 and solve for x. When doing this, we're going to have an ordered pair of x, 0 for our y value. Likewise, for our y-intercepts, to find those, we're going to set x equal to 0, and we're going to solve for y. From this, we're going to have x is 0 and a value for y, and we'll have the order pair 0, y. Right below this, we have an example that says find the x and the y intercepts. So again, in order to find our x-intercepts, we're going to set y equal to 0. In doing that, you're going to have 0 equals -x squared plus x plus 2. And from here, if this is too difficult to factor with a leading coefficient of a -1, that's okay. You can multiply every single thing on both sides by -1. And we'd have x squared minus x minus 2 equals 0. From here, I'm going to go ahead and use our guess and check method to factor this. And we end up with x for both of these factors with how they start. And the only things that multiply to 2 would be 2 and 1. One of these needs to be negative and one of these needs to be positive. The larger one will be negative since our middle term is negative. Again, I would check this to make sure that you did not accidentally factor this incorrectly. From here, we're going to set each of these factors equal to 0. This is our zero product property. And solving both of these, we get x is equal to 2 and x is equal to -1. So to write these intercepts, they need to be points. And so a point or an ordered pair we have as 2, 0. and the other one would be negative 1 comma 0. And these are going to be our x-intercepts. Likewise, we need to find the y-intercepts, and in order to do this, we need to set x equal to 0. This one's a lot nicer to solve. So we're going to have y equals negative 0 squared plus 0 plus 2. Solving this, we get y is equal to 2. So our y-intercepts at that point would be 0, 2. We have another example right below this that is also asking for us to find the x and y intercepts. So to find our x-intercepts, again, we're going to set y equal to 0. And doing that, we're going to have 0 equals x times the square root of x squared minus 1. Since we are multiplying here, we're able to set each of these factors equal to 0. So we have x equals 0, and the square root of x squared minus 1 equals 0. The first one is already solved for us. For the second one, I'm going to square both sides. Remember, whatever you do to one side, you need to do to the other side. So we have x squared minus 1 equals 0. This factors as x minus 1 or x plus 1. That difference is squares. And solving this, we're going to get x is equal to 1 and x is equal to negative 1. So from this problem, we actually have 3 x-intercepts. We're going to have 0, 0, so the origin. We also have 1, 0, and negative 1, 0. In order to find our y-intercepts, we're going to set x equal to 0. And doing that, we get y equals 0 times the square root of 0 squared minus 1, which just works out to being 0. So our only y-intercept will be at 0, 0. Right below this, we have some information on quadratic functions. And this is a function of the form f of x equals ax squared plus bx plus c, where a, b, and c are real numbers. The domain of a quadratic function consists of all real numbers, like we saw earlier. And a quadratic function is in standard form if we have f of x equals ax squared plus bx plus c, again, that descending order for our exponents. And this is going to make the graph of these creates what's called a parabola, which is the shape of the graph of a quadratic function that resembles a U shape. The sign of the leading coefficient, a, determines if the parabola is going to be opening up or opening down. And you can see that below. If a is greater than 0, we have a parabola that is opening up. And if a is less than 0, we have a parabola that's opening down. And again, a is that leading coefficient that we have that's in front of our x squared variable. The other thing to note is that with parabolas, and the useful part of these with business calculus, is that when you have a parabola that's opening upwards, this creates a minimum at that bottom of the parabola. And likewise, if you have a parabola that's opening downwards, we have a maximum that occurs at the top of that parabola. These special words for these points are called vertices or vertexes. And so this opens at a minimum for the vertex or opens down. It has a maximum at the vertex. So in order to find this vertex, which gives us mins and maxes, and in business calculus a lot of times we want to minimize a cost or maximize a revenue. And so that vertice or the vertex of the parabola, which is also called a turning point of the parabola, is the lowest point, a minimum on a parabola that opens upwards, and the highest point on or maximum on a parabola that opens downwards. To find the vertex of f of x equals ax squared plus bx plus c, we have a little formula here in order to find our x value. It's just x is equal to negative b over 2a. And then to find the y value that corresponds to that, we need to plug it back into our function. The example right below, I'm going to go ahead and circle, and we'll look at that one together in class. Another example that we have says Maria determines that when X hundred units of her product are produced, they can all be sold for a unit price given by the demand function P of X equals 60 minus X dollars. At what level of production is Maria's revenue maximized? what is the maximum revenue? And so in this problem, we're asking about the maximum revenue. And back in section 1.1, we had a formula for revenue, which is X times P of X. So that price that it's being sold at times X, which is going to be the number of units that we're selling. And for this problem, we don't have a revenue function, but what we do have is our demand function, P of X, that price, which is 60 minus X dollars. And we know that X is sold in hundreds of units. So in order to find our revenue function, we're going to have X times P of X, which is 60 minus X. And from here, I'm going to go ahead and distribute through my X and rewrite this in standard form. So doing that, we have 60x minus x squared, and then rewriting this in standard form, we're going to have negative x squared plus 60x. Since our leading coefficient is a negative value, we have -1, we know that this parabola is going to open down. And again, we know it's a parabola because we have an x squared as our leading value, and our leading coefficient's -1, which means that it's going to be opening downwards. And so this means that we're going to have a maximum at that vertex. We have a max at our vertex. So maximizing our revenue, this occurs at the vertex since our parabola is opening downwards. And so our vertex formula is x equals -b over 2 times a. And for this problem, we're going to have -b, and our b value here is 60, over 2 times a, which is -1. And so we have -60 divided by -2, or 30. And we need to make sure that we put units with this. And so since this is our x value, we know that this is in hundreds of units, as stated up above. And so we're going to have 3,000 units. Another way to say this is 30 plus 2 more zeros for the 100, or 3,000. So we'll say or 3,000 units. And it says, what is the maximum revenue? So at this point, we know how many units we have to sell in order to maximize our revenue. So in order to find that revenue, we need to substitute this back into our revenue function. So x is going to be 30. And so doing that, we're going to have -30 squared plus 60 times 30. And working this out, we get 900. So our units for this, since it says they are sold at a unit price given by the demand function, and that's in dollars, but since this is a unit price and we're going to be dealing with hundreds of units, so this is still going to be in hundreds of dollars. Or again, we can say that would be the same thing as $90,000.